As we progress in this unit, we're going to start looking at relationships that aren't truly proportional, but are linear. And this is a good example of something that is not proportional, but is linear. And so in our previous module, we were always able to, in a table, look straight across and think about what did I multiply this number by to get here? And you're like, well, I can't actually multiply 0 by anything to get to 144. And even if I look at here, this is 1, I can't multiply 1 by 132 and then get to this next number. And so that trick of moving straight across and multiplying by a constant of proportionality doesn't work when we're looking at linear relationships. But what we can start doing is looking at how our independent variable, that would be this one, independent, and the reason I know this is the independent or the x variable, is this is a time situation. And typically, a good safe assumption to start with is that time is typically an independent variable. But if I'm looking at this problem here, it says the amount of money at the end of each week and time this week. And I'm like, well, so is the amount of money going to depend on the week, or is the week going to depend on the amount of money? I'm like, oh yeah, the amount of money will depend on the week. And so we can label this as our independent and dependent. Did I spell it right? There we go. Or a y variable. So what we start to look for are these patterns. Is as we move down in the tables, I go this way, what am I doing each time as I move down this table? And so if I notice as I move down every time, my independent variable is adding 1. And if I look here, I start noticing that as I move down in this table, oh, I missed a row, there we go. Every single time, okay, so I'm like 144 minus 132. What's the difference between those two? Oh, that's subtracting 12. And if I look here, 132 minus 12, oh, that does get me to 120. 120 minus 12 gets me to 108. 108 minus 12 gets me to 96. 96 minus 12 gets me to 84. And so when we start thinking about our looking for patterns in linear relationships, it's a good useful strategy to start looking at how the rate of change between your y variables and your x variable changes. And so if we were to graph this, now we have our coordinates right here, 0 and 144 and 1 and 132 and 2 and 120. I could, even if I do a quick sort of unofficial graph, that doesn't use any proper tools like a ruler, but I could just do maybe like 20, 40, 60, 80, 100, 20, 40, 60, 20, I'll label this real quick, so that we can quickly just sketch out and see what this might look like. And this is like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is our weeks down here, and this is our money over here. And so at week 0, it is up here at 144, so let's say that's about there. At week 1, I notice it's at 132. That would be maybe here. Well, week 2 would look something, what's at 120? Would be like there-ish. Week 3 looks like it's at 108, so maybe it's there. Week 4 looks at 96, so maybe it's just a little bit less than 100. Week 5 is at 84, so maybe it's there. And my guess is if I had actually done this on graph paper, I would have seen that this had a very constant line. Because I did a sloppy quick graph, it doesn't look like it's exactly on a line, but I think that's my error, not a function of the graph. So that's why you should always use graph paper and figure out your appropriate scale when you go to graph this. Because that will help you determine, oh yeah, it is a linear equation because it does, or relationship because it does fall on this straight line. Versus over here, I had this point over here, that's just me doing a bad job graphing. So if I'm thinking about how do I write an equation for this, like I know it's a linear relationship because I can see it falls on a line. I can also see that there's a constant rate of change in my dependent and independent variables. We're going to use a sort of modification of the y equals kx. So our last unit, we talked a lot about y equals kx. This was our constant of proportionality. And what we're going to sort of add in this unit, we're going to get a lot more familiarity with it. We're going to modify this to look something like this. And this M here is going to represent the slope. And we're going to talk later on about what that particular thing is, but it's very much related to this constant of proportionality. And so this number here, this B, is going to represent where it crosses the y-intercept. And so the way we can find that in a table is by looking for this place where it's 0. And so if I wanted to write an equation to represent this relationship, we'll get more into this as we keep going. For now, what I want you to notice is, okay, it's a decreasing, and so my line is going down. It's crossing here at 144. This is our B, what we call our y-intercept. And then our slope is our rate of change, and so every time we're losing 8. And so the actual equation I would write for this one is y equals negative 8x plus 144. And we'll get a lot more practice with this as we go through the unit. But for now, the big takeaways I want you to find is if you're trying to identify, is this thing a linear relationship, you're not going to always be able to multiply straight across. But what you will be able to do is look for a constant rate of change, and maybe it's subtracting 12 and adding 1, or maybe it's adding 3 and subtracting 7. It can be totally different. What you're really looking for is there something that's constant in your y's, and is there something constant in your x's? A linear equation will always follow this general format, where it will have some constant amount that you're either adding or subtracting each time, multiplied times your x, and then some other number added to it, or maybe subtracted to it, where it crosses, and it's sort of like an initial starting fee. So like here, it looks like they started with $144, and they're losing $8 per week. And so we can start predicting what would happen over time. So big takeaways, in a table, look for the constant rate of change in your dependent and independent variables. And so it's drawing arrows and figuring out off to the side how much you are changing per row. In a graph, a linear equation will always follow a straight line. It does not have to go through the origin, and it does not have to be an increasing. It can be a decreasing. From an equation, it's always going to follow this format of a y equals mx plus b.